Relative orientation allows you to orient two cameras for 3D analysis without a survey of points in the background. All that is needed is 6 points with a known distance between any two of them. Relative orientation results in an initial coordinate system that is based on the sensor of one of the cameras, and in turn this means that another coordinate system must be set up for test purposes. In this tutorial we're going to bring in two images, the left and the right. Because we are working in 3D, after checking the name and frame frequency, we need to set the focal length of each camera correctly. The resolution, pixel size and optical center have been brought in correctly from this image sequence in this case. Now we will repeat with the right image. Now we are going to bring in the time overview panel to ensure that we have the sequences in synchronization. Now we are going to put 7 reference points in each of the two images. They must have the same names, and in each image they must be attached to the same points. To obtain accurate positioning, we will reset the points to the quadrant targets so they lock onto the targets. We will use the Show Window option to check that they're all set accurately. If they are not, and because it is a quadrant market, you will need to use the Alt key if you want to adjust them. Now that we have them all placed, we can go to the camera orientation, the relative orientation, and set up the camera using 2 points in the image that we know the distance between, in this case 15.36 inches apart. Now the cameras are oriented. You will notice that the left camera has an XYZ of 0, 0, 0, and the same with the roll pitch yaw. The other camera is referenced to the first one. The parallaxes look good, and the distance between the two cameras, the baseline 2.56, checks out with what we noticed when we set up. We could now go in and do a 3D tracking. However, first we're going to set up a new coordinate system called the tabletop, which we can use in our test. We are going to set point 7 as the XYZ 0. We're going to set point 7 and point 3 as the x-axis, and we're going to set point 7 and point 2 as a further definition of the xy plane. Now we will turn off the reference points and add a new point to the tip of the foiling pointer that we want to track in 3D. We highlight the image and we add the point, highlight the point, and then place it. Now we can use the show window to get a good view of the point, and we can start tracking. Details of tracking were in the 2D Getting Started tutorial, so we will run through this quickly. As you can see, it has been tracked, and now we will go and produce a graph, 2D graph, that will confirm that we have tracked accurately before we try to do any 3D in it. The 2D graph for point 8, the point we added on the pointer, now looks good, so we can discard that. Now we will reset the framing to the first frame in which the pointer appears in the right frame. Add point 8 to the right hand image, and you will see that the line crossing the screen there marks the line on which that should fall. If that falls accurately, then the 3D is well set up and we can begin to track. Again, we will skip the tracking. We now have that tip of the pointer tracked in both the left and the right images, and we can plot 3D diagrams at this point. To begin with, we will take the 3D position of point 8, add it to the graph and plot the z-axis, the vertical axis. As you can see, we now have that vertical plot. Now we'll go back to the diagram, get a 3D diagram, and add the point 8 to that diagram. Again, you can see that the point is marked in the 3D diagram, and all three graphs track together.